Hi friends, welcome back to yet another video, a fairly very simple problem. So let's get started. As usual, I request all of you to pause this video, read the question very carefully, try to do the problem on your own. And if you are not able to solve, then just come back and see my explanation. So in this problem, we have a solid cube of length 1 meter. That makes our calculation fairly easy. What happens is the cube is constrained all around and is heated uniformly to 42 degrees Celsius. And then they are asking what is the magnitude of the volumetric mean stress in MPa induced due to heating. So the first question is, let me ask you another question before we start solving this problem. I remember this question was asked to me sometime in some exam. I think it was asked in UGC NET for Engineering Sciences sometime back when I was giving the exam. So you have a beam like this. Maybe I can further reduce this complexity over there, and then I have a pinned end over here. Then I have a simply supported end over here. What happens when I increase the temperature of this system by 50 degrees Celsius? Let's say the length of the system is capital L, then alpha is my coefficient of linear thermal expansion. Coefficient of linear thermal expansion is alpha. What happens? The answer is it won't cause any stress. Why? Because we are not limiting or we are not obstructing the deformation of the system. But in this question, the cube is constrained. So we are not allowing the solid cube to expand. That means there will be a volumetric mean stress which will get developed in the system. So thanks to the way how we have defined the bulk modulus of elasticity, we know there are three modulus: shear modulus, Young's modulus, and then we have this bulk modulus. So the bulk modulus is defined in such a fashion that it's fairly easy to compute that hydrostatic mean stress. So it is given like this, where delta P is the hydrostatic stress that you're applying on the body uh, on all directions. It's not like you're applying in one direction. If this is the cube, you're applying it in all directions, all three directions. Okay, and then the cube is getting, or it's undergoing some kind of volume change. This is the volumetric strain that this cube undergoes. Delta V divided by V, where V is the original volume and delta V is the change in volume. So in this particular problem, we know this quantity. They're asking us to find out this quantity. Then okay, now the question arises, when the temperature of the body, temperature of the cube in this particular example, is increased by 10 degrees Celsius, what exactly happens to the cube? It suffers a volumetric dilation or a volumetric change, but in this case it is restrained. It is not allowed, we are not allowing it to happen. So that means a corresponding value of hydrostatic stress will be developed inside the system. So think of a scenario when you didn't have any constraints and it was allowed to expand, it was allowed to move in all directions, in whatever way it wants to move. Then if you increase the temperature by 10 degree centigrade, what would have been the delta V? So before we uh, go ahead, so the volumetric strain can be written as a summation of the longitudinal strains. This is fairly easy because we know, let's say cube is having the same dimension in all directions. even though if it is not, if even though if that was not the case, let's say the volume is a product of three quantities, then also dv by v will be simply a summation of dx by x plus dy. I can write it fairly in a far more neat way, I guess. Oh, so for those who don't or not so comfortable with the math, I can explain that. So the volume can be written as a product of the three dimensions v, x, y, z, and if you take the logarithm on both sides, you end up with this expression: log e x plus log e y plus log e z. Log e z. Now if you take the derivative, when you derivative of log x is 1 by x, you will end up with this expression. Okay, so I made a mistake. Okay, there is no d here, there is no d here. Then it is not z, it is y. Okay, so this is your epsilon x, this is your epsilon y, strain in the y direction, this is your epsilon z. These are your normal strains in the three mutually perpendicular directions. So if you add them up, you get the volumetric shear strain, volumetric strain, you can say. So that is simple. That's how you get this expression. Okay, you don't have to put that minus. Let's say we don't don't have to get you don't have to get confused with this units whatever I'm using. But the concept is, had the cube been allowed to expand, then it would have seen this much of a volumetric strain. In fact, this much of an increase in volume. I'm removing those minus symbols from all these expressions. So this is the volumetric strain that this system would have experienced. Now, to compute the hydrostatic mean stress, it's fairly easy, because you remember the first expression we wrote, the bulk modulus is defined as minus delta P divided by the volumetric strain. Oh, I had this doubt why this negative sign. Oftentimes I used, but this is because of the fact that usually in hydrostatic state of stress you have this things pointing inward. That's why the minus p comes into the equation. Make sense? You don't have to bother too much about the simple anyway. Now the rest of the things is fairly easy. You know this value, you know the bulk modulus, but one thing, as I usually say, have consistent set of units. See, here I plugged it in MPa. Okay, again a small correction. In the question it was given 200 GPa, I changed into MPa so that I get the stress in Newton per mm square, or in MPa again. So this is a consistent set of unit that I usually use. It's up to you, you can use whatever units you want, but again pay attention to the question, because they would have asked you in certain units. Like see the question here, in here you can see they are asking you what is the magnitude of the volumetric mean stress in MPa. They are not asking you in Newton per meter square. Be very careful before you plug in those numbers during the exam. Clear? Thanks for watching. So the key concept is, uh, when does the thermal strains or raise in temperature causes a stress? In this case, it was not causing any stress because it is allowed to move. But in this case, it was causing some stress. Why? Because it was constrained in all directions. Make sense? Thanks for watching.